Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on complex analysis, lecture number 10, in which we will discuss problems on analytic functions, Laplace equation, harmonic functions, and different types of tricks to construct the analytic functions. Now we define Laplace differential equation. Let phi xy be a function of two variables x and y such that second order partial derivatives of the function exist and they are continuous. Then the equation partial derivative of second order del 2 phi by del x square plus del 2 phi by del y square equal to 0 is called Laplace differential equation. Now we shall prove a theorem. Real and imaginary parts of an analytic function satisfy Laplace equation. Prove. Let fz equal to u plus iv be an analytic function in some domain D. As fz is analytic, therefore ux equal to vy and uy equal to minus vx implies that del u by del x equal to del v by del y and del u by del y equal to minus del v by del x. This is number 1 and this is number 2. Differentiating 1 with respect to x partially, del 2u by del x square equal to del 2v by del x del y. Again differentiating 2 with respect to y partially, del 2u by del y square equal to minus del 2v del x del y implies that del 2u by del x square plus del 2u by del y square equal to del 2v del x del y minus del 2v del x del y implies that del 2u by del x square plus del 2u by del y square equal to 0. Therefore, uxy satisfies the Laplace equation. Similarly, we may show that del 2v by del x square plus del 2v by del y square equal to 0. Therefore, vxy satisfies Laplace equation. Now we define harmonic function. Any function of x and y which has continuous partial derivatives of first and second order and satisfies the Laplace equation is called harmonic function. Let fz equal to u plus iv be analytic. Then we know that u and v are satisfy the Laplace equation. Therefore, u and v are harmonic functions. U and v are called conjugate harmonic functions or simply conjugate functions. Now we shall describe the method of constructing an analytic function. Let fz equal to u plus iv be an analytic function. Therefore, ux equal to vy and uy equal to minus vx by Cauchy-Riemann equation. By Cauchy-Riemann equation. Let only uxy is given, then we have to find vxy and then construct fz equal to u plus iv. Since uxy is given, now with the help of this we have to find v. Since v equal to function of xy, v is a function of xy, implies that dv equal to del v by del x dx plus del v by del y dy. This is vx dx, vy dy. Since vx means minus uy equal to minus uy dx and vy means ux dy. Let this is number 1, this is number 2. Let minus uy equal to m and ux equal to n, then right hand side of 2 will be m dx plus n dy. Now we examine that this is exact differential or not. For this del m by del y, del by del y, m is minus uy, that is minus del by del y del u by del y. This is equal to minus del 2u by del y square. This is number 3, let, and this is number 4. Now del n by del x equal to del by del x n is ux equal to del by del x del u by del x equal to del 2u by del x square. This is number 5. From 5 and 4, del n by del x minus del m by del y equal to del 2u by del x square minus del 2u by del y square equal to this is minus del 2u by del x square plus del 2u by del y square equal to 0, since uxy satisfies Laplace equation. So we get that. So we get del n by del x minus del m by del y equal to 0 implies that del m by del y equal to del n by del x. This is the condition for exact differential. Therefore, m dx plus n dy is exact differential. That is total differential. CL. So we may find V by integrating m dx plus n dy. As we have obtained V, then we may construct Fz equal to u plus iv. That is an analytic function. Here already u is given, and with the help of u we find v, then we get fz equal to u plus iv, which is an analytic function. Now we solve a problem in which u is given. We have to find the analytic function fz equal to u plus iv. So firstly we have to find del u by del x and del u by del y. Solution. Del u by del x equal to multiply product of two parts. First differentiate e to the power x, and this remains same, x cos y minus y sin y, plus this remains same, e to the power x, differentiation of this x is 1 cos y, 1 cos y minus, there is no x, so this is 0, equal to e to the power x x cos y minus y sin y plus e to the power x cos y. Now we find del u by del y. For this, e to the power x is treated as constant. We differentiate this e to the power x constant, and differentiation of cos y is minus sin y minus product of two function, differentiation of y is 1 sin y minus y, differentiation of sin y is cos y. This is equal to e to the power x minus x sin y minus sin y minus y cos y. This is number 1, this is number 2. Now v is the function of xy, dv equal to del v by del x dx plus del v by del y dy. This is vx equal to uy minus uy dx, and ux equal to vy. This is ux dy. This is equal to minus uy is this quantity, means minus term, all are negative terms, so positive term. So e to the power x sin y plus sin y plus y cos y, and this is uy, and ux here, ux is e to the power x and with dx, here we have dx also, plus ux is e to the power x cos y minus y sin y plus e to the power x cos y and dy. This is m dx plus n dy, where m is this part, where m equal to e to the power x sin y plus sin y plus y cos y, n equal to e to the power x cos y minus y sin y plus e to the power x cos y. This is number 1, 2, and this is 3.
Since we know that equation 3 is exact differential,
so v will be equal to integration, here y constant, m dx plus integration terms of n which does not contain x x integration dy. So this will be equal to y constant. M is e to the power x sin y plus sin y plus y cos y dx plus, here each term of n contains e to the power x and here also x. So we get no terms free from x. So 0 dy. Implies that v equal to, here we integrate this term taking y as constant. We consider this is the first term and e to the power x is the second term. So integrating by parts, first term x sin y plus y cos y, first term. Integration of second, integration of e to the power x minus integration of differentiation of first term and integration of second term e to the power x. Now this remains same. Integration of e to the power x is e to the power x minus differentiation here with respect to x, and y's are treated as constant. So differentiation of x is 1 into sin y and these are treated constant. So differentiation of this will be 0. Only we get 1 into sin y. Now integration of e to the power x is e to the power x dx. So equal to, we write this term e to the power x minus sin y is constant with respect to x only, y is constant, here y constant, here y constant, and here also y constant. Here y constant. So we may take sin y out of this integration and we integrate e to the power x. Integration of e to the power x with respect to x is e to the power x. So sin y e to the power x. Now we multiply each term with e to the power x, and here also this term and this term cancel out, only remains e to the power x sin y plus e to the power x y cos y. This is the value of v. Now we put fz equal to u plus iv. Value of u is e to the power x cos y minus y sin y plus I, here v is e to the power x sin y plus e to the power x y cos y. This is the value of fz. Now we change the value in xy in terms of z. Now fz equal to e to the power x cos y minus y sin y plus I x e to the power x sin y plus I e to the power x y cos y, as we have taken e to the power x common. So we may write this fz. Now here we take x common, x cos y, here x common, so here remains cos y, here remains I sin y. We make minus 1 as I square y sin y. This is I y cos y. Here this is remain same. Here we take I y common. Here cos y plus I sin y. So cos y plus I sin y common. Here x plus I y. Cos y plus I sin y is e to the power I y, and x plus I y equal to z. So this is, we add powers, base same, e to the power x plus I y into z. This is e to the power z into z equal to z e to the power z. We may also add some constant, as during the period of finding v we have integrated there. So we use here c. Therefore function of z is z e to the power z plus c, and we find the analytic function. Ultimately with the help of u we find v, then fz equal to u plus iv, and finally fz equal to z e to the power z plus c. Now we describe Milne-Thompson method to find analytic function. When we know the only one part of analytic function u x y, as let fz equal to u plus iv, only u part is known, then with the help of Milne-Thompson method we find the analytic function very easily. That is, we may find fz equal to u plus iv. U is known and we have to find both u and v very easily. We know that if fz is analytic, then f dash z equal to ux plus ivx. We know that ux equal to vy and uy equal to minus vx. Ux minus I uy. Uy equal to, since uy equal to minus vx. Let this is equal to function of xy, and this is another function of xy. Replace x by z and y by 0. Then we get f dash z equal to phi 1 z0 minus I phi 2 z0. Then right hand side will be in terms of z, and then we integrate this fz, integrating both sides, we get the analytic function fz. Now a problem is given, so that the function u equal to x cube minus 3x y square is harmonic, and find the corresponding analytic function. Firstly, we show that this function is harmonic. Solution. Del u by del x equal to 3x square minus 3y square. Del 2u by del x square equal to 6x. Again, as there is no x, so here 0. Again, del u by del y equal to del u by del y equal to 3x into 2y. Del 2u by del y square equal to, again differentiating with respect to y, here we get here minus 3x into 2, that is minus 6x. Del 2u by del x square plus del 2u by del y square. Del 2u by del x square is 6x, and del 2u by del y square is minus 6x. This is 0, therefore u is satisfies the Laplace equation. Therefore u is harmonic. Now we find the analytic function. Since del u by del x equal to 3x square minus 3y square, we consider del u by del x as phi 1 xy. This is equal to 3x square minus 3y square. Now we use the Milne-Thompson method to find the analytic function. For this, we have to construct phi 1 z0. In place of x, we write z, and in place of y 0. Here z square minus 3 into 0, that is 3z square. Phi 1 z0 equal to 3z square. Del u by del y is minus 6xy equal to phi 2 xy. Now, according to Milne-Thompson method, we construct phi 2 z0 equal to minus 6 in place of xz, in place of y0, that is 0. Now, f dash z equal to phi 1 z0 minus I phi 2 z0. Phi 1 z0 is 3z square minus I phi 2 z0 is 0, that is 3z square. F dash z equal to 3z square. Integrating both sides, single variable here z. So integration is very easy. Integrating, we get here fz, and here integrating z square, z cube by 3 plus constant, 3 cancel,
equal to zq plus c, that is fz equal to zq plus c is the required analytic function.
Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.